All right, we will go over the divergence theorem in this video. Here's the main statement of the divergence theorem. We're assuming that things are all right, that there's nothing weird going on, that there's some kind of continuity, even though the continuity may be piecewise. Still, we have some kind of continuity, as in this case, we have continuity of the surface. What we are doing is taking a triple integral over a solid and converting it into a double integral. So we are decreasing the size of the dimension of the integration. Now, in order to do that, we have to have an anti-divergence of a vector field F. If we can find the anti-divergence, then we can go in this direction, or if this is too difficult, then we can go in this direction. It is true that this is somewhat similar to the fundamental theorem of calculus, and you guys know that very well. If you have the integral from a to b of the derivative of a function, and you want to find the integral, well, the fundamental theorem of calculus says you can do b minus a, like so. And you have to find the antiderivative of this function in order to do that. So here is the same kind of situation. We have to do the anti-divergence of f, and that's why this is called the divergence theorem. Stokes' theorem is similar to this, and so is Green's theorem, except that we have different dimensions. And so is the fundamental theorem of line integrals. So all of those theorems are of the same kind. We are integrating over the boundary. So this is the solid, integrating over the solid versus integrating over the boundary. The boundary of a solid would be its surface. Here we have a triple integral, we have a double integral. Here we have a single integral, and then we have no integral when we find the antiderivative. By the way, not all functions have necessarily anti-something. Now, some students ask, well, that means that we have to always go in this direction. Not necessarily. We could go in whatever direction makes the work easier. So for instance, if we were integrating something that was complicated, rather something with a lot of faces, then I wouldn't want to do the surface integral, because then I would have to split this problem into 6 problems: the top, the bottom, the front, the back, the right side, and the left side, as we face this cube. If this is the solid we want to integrate over, I would probably just keep it the way it is. I wouldn't change it into a surface integral, unless this function is very simple. See, it's not clear which way it's going to be easier. On the other hand, doing this may be simpler using a surface integral, because I can parameterize the whole thing with one function, with one function. We don't have to split this up into different surfaces. This is one surface. So from this perspective, that would be easier, I believe, than doing the divergence. Yeah, the divergence could be more complicated. Doing the triple integral in this case versus this case. No, I misspoke. This would be easier, I think, in general, but not all the time. And this would be easier. There we go. That's what I wanted to do. Now, mind that Stokes' theorem says that if this in turn happens to be the curl of another vector field, then a closed solid, the integral over a closed solid would be 0. If we have a closed solid. That's what I suggested in the last video, 53401, that if this is a closed solid and this happens to be the curl of another function, then we would get 0. So for instance, just to give an example, let's say we have f is a 0, 1, 2. So those are a bunch of vectors going kind of sideways, so the slope is actually, but all of them going into the same direction. Let's see if we can find an anti-curl of this guy, and I believe we can. So an anti-curl of F would be, let's see, I think Z, if we want Z, 2x and 0 will do, 2x and 0. Remember in the last video, in 53401, we saw a little bit of this. Let's see, so 0, 0, yep, that gives us a 0, and then 0, 1, yep, that gives us the 1, and then 2 and 0, yep, I believe this is one anti-curl. And since we can find an anti-curl, then automatically the surface integral over this solid would be 0, because anything that goes in has to go out, and yeah, and consequently this is interesting. If you find the divergence of this f, the divergence of f, of course, is the gradient applied to, well, dotted with f, and that would be, of course, the vector 0. No, not the vector 0, the scalar 0. No vector at all. Because the derivative of 0 is 0, the derivative of 1 is 0, the derivative of 2 is 0, so 0 plus 0 plus 0 would be 0. And so if we apply the divergence theorem anyway, we would immediately get 0 here without thinking about last video or anything like that, the Stokes theorem. And so we could get 0 from the two ends, from the divergence theorem or Stokes theorem. If we have this situation, we would get 0. That is, I think, interesting. So we're not going to do this example because that example immediately gives us 0. We're going to do an example where we still have the same box. So we're going to call it, I'm going to call it the unit box. Let's call this example 1. Yep. And we want to find the double integral of the f with respect to the surface, across the surface. And the surface is going to be what I call the unit cube. So it's a cube that is 1 unit on each side. Yep, like so. Starting, one of the vertices is going to be at the origin. The opposite, the diametrical opposite vertex would be 1, 1, 1. So 0, 0, 0 to 1, 1, 1. Those are two opposite vertices of this. And I have to tell you, f with f, let's say f is x squared plus y squared plus z squared. There we go. So the vectors, I'm sorry, I didn't mean plus, I meant comma. This has to be a vector field. Yep, let's put a z there again, comma, comma, parenthesis. There we go. So I was going to draw it, and that's when I realized this doesn't make sense. So up here, we would have 0, 0 up, and here 0 to the right, and this way, and then vectors are going to get away from the origin. That's, yep, because we have squaring. Well, on the first octant, which is where we are, the vector field gets away from the origin. Yeah, because all of those are going to be positive regardless, or 0, even in the negatives, yeah, we're going to have something weird going on the transitions. But anyway, I think, anyway, so this is going away. And what is the, so this is what we want. And the question is, if we want to do it with a surface integral, as is, we would have to split this up into different surfaces, the top, the bottom, the front, the back, the right, and the left. Or we can use the divergence theorem. So this is equal to, by divergence theorem, the triple integral of the divergence of this guy, which of course is 2x plus 2y plus 2z. Yep, derivative of this with respect to x plus the derivative of that with respect to y plus the derivative of that with respect to z over the volume. And let's call this the solid E, solid E. So over E, which really means the triple iterated integral from 0 to 1, again, 2x plus 2y plus 2z with respect to x, with respect to y, with respect to z. That's z. And well, with respect to x, we get x squared over 2, but there's a 2 in front, so that is just x squared. Plug in 1 and 0, and you get 1. I'm going to make this a little easy on us. 1 plus 2y plus 2z. The reason why we get 2y back again is because we're integrating x from 0 to 1. Had we were integrating x from 0 to 2, for instance, then we would end up with 4y instead of 2y. So watch out. This is going to turn out fairly easy because of the zeros and the ones. Otherwise, you got to pay attention to what is different. Now, so integrating 1 from 0 to 1 is going to give us 1. Here, we're going to end up with y squared over 2 times 2, so just y squared. We're going to plug in 1 and 0 and subtract, so another 1. And here, the 2z, it will become 2zy as y goes from 0 to 1. So again, we're just going to end up with 2z. So we're integrating from 0 to 1, 1 plus 1 plus 2z with respect to z. And that's going to give us 1 plus 1 plus 1, which is going to give us 3. All right. So the surface integral of this vector field, so the flux of this vector field across the whole unit cube is going to be 3. There it is, 3. All right. And we use, in this process, the divergence theorem. So this one doesn't have a name. I don't know a name of a person as Stokes. Why didn't we call the Stokes theorem the curl theorem? Just like this one is the divergence theorem. And Green's theorem, well, then I have to think about what we would call Green's theorem. But anyway, so this is page 2. Let's do example 1. Again, without the divergence theorem. All right, so that's going to be a little bit of work. Excuse me. Excuse me. So we got, again, our unit box. So we're going to split this into 6 surfaces. 6 surfaces. So we're going to have the top, the bottom, and then the front, the back. Oh, the back. I'm just going to call it back. So the back, bottom. So the right side and the left side. Okay. So we're going to do the double integral of, so without applying the divergence theorem, we're going to do the double integral of x squared, y squared, z squared, surface double integral over the top. I'm just going to call it top. All right, so we need to parameterize the top. the parameterization of the top is pretty straightforward, x, y, 1. So r sub x is going to be 1, 0, 0, which is equal to the vector I. R sub y is equal to 0, 1, 0, which is j. And then when we cross r sub x, cross with r sub y, we're going to cross I and j, and everybody knows that that is going to be k, or 0, 0, 1. Or you can just do the multiplication yourself, 0, 0, and then 1. Yep. Yep. So that means we're going to, when we do the dot product, we should write down the, so it's still the top, although we could have gone from 0 to 1 already. But we're going to do this, x squared, y squared, z squared. We're going to multiply with 0, 0, 1 with respect to the area. You know, x is going to go from 0 to 1, and so is y. But we're going to end up with just z squared, double integral of z squared, dy dx. It doesn't matter which one first because we're going from 0 to 1. And z squared, mind that this is x, y, and this is z. Z in this case is 1. So we're really integrating, double integrating from 0 to 1, 0 to 1, 1 dy dx, which is just 1, because this is the squared that is 1 by 1, and we're finding its area. In fact, I could have figured that out back here when we thought of the area. But anyway, this is going to be 1. So the top is 1. Top is 1. All right, what about the bottom? So we want now the double integral, the surface integral over the bottom of this unit cube of x squared, y squared, z squared with respect to the surface. Now that means we need to parameterize the bottom. The parameterization of the bottom is going to be pretty much the same way as the top, x, y, but the bottom will have a z coordinate of 0 across the bottom. That's why it is the bottom. Okay, so we repeat everything. The only difference is that instead of 1, we're going to have a 0 compared to the top surface. But that does not affect the cross product or the partial derivatives. So we're going to end up with 0, 0, 1 again, dotted with 0, 0, 1 with respect to the area. So we end up with z squared, double integral of z squared with respect to the area over the bottom. Well, yeah, bottom. But the bottom, this is the parameterization of the bottom. The z in the bottom is 0. This z is going to be 0, 0 squared. So this is the double integral over the bottom of 0 squared with respect to the area, and that's going to give us 0. So we piggybacked on the top because the parameterization was very much the same, except that this one has 1 and this one has 0. And that caused this guy to be 0. So far we have the top plus the bottom, which is 1 plus 0. So that is interesting. The bottom did not contribute to the flux of the vector field. We're finding the flux, after all. The flux of the vector field through the top is 1, through the bottom is 0. That's information we did not get when we used the divergence theorem. The divergence theorem gave us the answer, 3, but without telling us how much each one of the surfaces contributed to the total flux. Now, we can start beginning to put this together. This 1 probably came from the top and nothing from the bottom. All right. So let's continue with this surface or surfaces. Let's do the front. So remember, the front is this guy, which we're going to parameterize as r of uv, because using x and y, we could, is kind of weird. So x is fixed at 1. And then we can just set u and v to be those two. So u goes from 0 and 1, and so does v. It's important to know. I took that for granted in the previous page here because we are right on top, and this is the unit cube here. We should emphasize, because this is the front face of the front from our view, it is its front. Of course, that is relative. So the double integral of x squared, y squared, z squared over the surface integral, rather, over the front. Oh, we got to do more to this. We got to find r sub x, which is going to, or u rather, not x, u instead. This eraser, I don't want to promote it necessarily, but I like it because I don't have to wait to dry up. If you use the liquid one, then you have to wait, and that would make these videos very, very boring. Right now, they're very exciting. And so this is J, this is K. When we cross multiply J with K, we end up with I. So the cross product R sub U crossed R sub V equals 1, 0, oh, you can double check. So this is equal to the double integral. Let's see what we get. X squared, Y squared, Z squared, 1 dotted with 1, 0, 0 over the area. The area corresponding, so when we say A, we mean this, corresponding to that. So this is the front. And we're just picking up x squared, but x is 1, mind, this is x, and this is y, and this is z. So that's why it is weird to use x and y. We could have, but then it would get confused with this x, with the actual x, y, and z corresponding to the coordinates. So x is 1. So we're integrating just 1 squared with respect to the area over the front. Well, yeah, let's just keep it here this way. And that's going to give us 1. So this, the flux of this vector field through the front is going to be 1. Now, if we go to the back, so the back is going to be here. The only difference between the front and the back, so we have a new r, uv, is that we're going to end up with 0 uv. Everything else is going to be the same. The partial derivatives are going to be the same vector. So on the back, so this is a new thing. So the double integral, or the surface integral over the back. This is weird because now we changed this. Anyway, just keep in mind, this is A. Let's call that the region developed by this. Let's label it as D, because that makes me feel there's something wrong, because we're changing from X, Y, and Z into UV. So technically speaking, we have a different set of variables we're using. And let me go back to this. We want to be proper. Here we were, because we actually changed from 0 to 1s. And here there's not too much of a problem because we're using a trivial, which means x and a trivial parameterization, which means that x and y remain the same way. Here, we're not using the same x and y, we're using u and v. So I'm using d to refer to the fact that the region is, so yeah, we shouldn't use a. The region we're integrating over is d, which would be in a different plane. Anyway, the back, the only difference with the back is that the x value would be 0. So when we do x squared, y squared, z squared, ds, we're going to end up with, again, x squared dA over d. But in this case, x would be 0. So we are double integrating over the 0 squared dA, which of course is going to give us 0. All right, so the front gives us 1, the back gives us 0. You see where this is going? Because we know the answer is 3. And how do we account for 3 if we have 6 faces? Well, it could have happened that we would have, there's all kinds of combinations. Each face could have been a half, or maybe the front 3/4 and the back 1/4. Who knows what combinations? Or the front could have been, I don't know, 16, and the back could have been negative 15 or something like that. Some kind of combination. There's many combinations that end up with a 1 by adding two numbers. But we didn't know the combination was going to be 1 and 0 on the front and the back. And I'm assuming that on the right, or I'm guessing that on the right, we're going to get 1, and on the left, we're going to get 0. So I'm going to ask you to please do the other two faces. And in fact, I did it earlier. And sure enough, on the right, we're going to end up with 1. On the left, we're going to end up with 0. So that is interesting. The flux of this vector field over the unit cube is going to give us 1 on the top, 1 on the front, 1 on the right, but then 0 on the other 3 faces, which means the other 3 faces could have been gone. And just the surface integral, the only thing that matters in this particular solid or surface are those 3 faces. The other 3 faces we could do without, and we still have the same flux. Yeah, and the reason is because on those surfaces, the vector field actually is parallel to the surface itself, and consequently nothing gets through those surfaces. Isn't that interesting? However, the point I wanted to make, though, is that here we would have to do 6 different surface integrals, one by one, even if we take some shortcuts to get to a second one after the first one. But if we use the divergence theorem, boom, we're done in, where did we finish? No, that's not it. That was without, here's the example. This is all it takes using the divergence theorem. So the divergence theorem is way faster. In this case, I'm not stating that divergence theorem, apply the divergence. And even, what do we mean by applying the divergence theorem? There's 2 sides to the equation. Sometimes you're here and you want to go there, and sometimes you're here and you want to go there, and one may be easier. It's not as clear necessarily as that. If you have an antiderivative that you can find easily, then sure, that's enough. I mean, that's easy. But if you don't have an antiderivative, maybe a numerical approximation will be good enough. That's where we need to think what is easier. And this is not always easier. If we have an antiderivative, sure, no problem. Same thing here. We don't know in advance which one is going to be easier. Sometimes if we stay where we start, that's actually going to be easier. Okay, let me get started with a second example. Example 2. All right, let's do the same integral over the same vector field, x squared, y squared, z squared, with respect to the surface. But the surface will be the unit sphere. So a sphere centered at the origin with radius 1. So you guys know the equation of a unit sphere. Do I want to do a triple integral? Or do we want to do a surface integral? Let me go back to example 1. And what was easy? The easy thing was to do the triple integral. Yep, because we went from 0 to 1s. Here, I'm gonna guess leaving it as is gonna be easier. We need to parameterize the surface, and a good parameterization to use when we have a unit sphere. So our a unit sphere, a good parameterization perhaps would be UV. It's a unit sphere, so we don't need a radius. Maybe sine of U, cosine V, sine U, sine V, and cosine U will do, where U goes from 0 to pi, and V goes from 0 to 2 pi. And of course, if you remember well, this is very much the same thing as the spherical coordinates, because it's very easy to come up with a sphere using spherical coordinates. Let me double check my notes to make sure I changed them correctly. Sine U, yeah, there it is, sine U, cosine V, sine U, sine V, because there's a couple different combinations that result in the same, depending on how we are rotating half circles. But this one is consistent with the spherical change. So there's a parameterization of the sphere. And remember, we have to do a few things before we change this into an iterated integral. This surface integral changed into an iterated integral means that we have to do r sub u. Boy, this is going to be cosine of u, cosine v, cosine of u, sine v, and sine, negative sine u. R sub v would be, so sine, cosine, so negative sine u, sine v, sine u, cosine v, 0, because we're doing derivatives with respect to v. Our u crossed our v, man, this gets, it's going to be a little bit long. So 0 plus sine squared of u, sine squared of u, cosine v, and then we're going to do 0 minus that, but then there's an extra negative, so we will have, just got lost for a moment. Zero, minus, yeah. So sine squared of u, sine of v, comma, and then this next coordinate will have two terms. They have cosine of v in common, but then sine of u, cosine of u, sine u, cosine u, boy, and then cosine of v, whoops, squared. Cosine v squared, boy, and then those two plus, because there's an extra minus here, sine u, cosine u, sine squared. Sine u, cosine u, and then sine squared of v. Sine squared of v. Okay, close parenthesis. So those are the three components of the vector. By the way, we have cosine squared and sine squared. So those two consolidate into just one. So we really have let me double check something real quick here. That minus, yeah. So sine squared u cosine v, sine squared u sine v, and then sine u cosine u. All right. So let's start a new page. So the double integral, we're still in example 2. The double integral of x squared, y squared, z squared with respect to the surface over the unit sphere will be equal to the iterated integral. Okay, so x squared is this guy squared. So cosine u cosine v squared, man, cosine u squared cosine v squared, comma. I'm sorry, that is supposed to be sine. Yep. Sine squared of u cosine squared of v, because I'm looking at this guy. Sine u cosine v plus sine u sine v, or not plus, comma, sine squared u sine squared v, comma, and then z squared is cosine squared of u, cosine squared of u. Close the parenthesis of the vector. Then because of the ds, that's where we need to do the ru, r sub v, cross them up, and then we end up with this. So we're going to do the dot product. Boy, this is getting more complicated than what I anticipated. Sine squared u cosine v, comma, we just did this, sine squared u sine v, and sine of u cosine of u, close parenthesis, with respect to u and v, as u goes from 0 to pi and v goes from 0 to 2 pi. Watch out, because one goes from 0 to pi while the other one goes from 0 to 2 pi. Whoa, 0 to pi, 0 to pi. Now we're going to consolidate that into one scalar function of u and v. So let's keep track of those guys. So that and that gives us 4 sines, sine to the 4 of u, cosine cubed of v, plus sine squared of u, that's the second component, sine squared of u, so that's sine to the 4 of u, sine squared of v, and sine of v, that gives us sine cubed of v, plus, and then the last component is cosine squared u, and then another cosine of u, so we have sine u cosine cubed of u, du dv. Okay. Now we're going to use a little trick about cubing functions. If you have, let me do this here. If you have sine, it doesn't matter what you have, sine or cosine. So sine looks like this over one period, 2 pi. And this is sine cubed of x, whatever the variable is. If you do, no, just sine of x. If you cube it, on the other hand, sine cubed of x. Boy, that looks not very good. There, just the sine by itself. is that. But if you cube it, you're going to end up pretty much with the same thing. There's a deformation of the, there's going to be more changes of concavity, but we have very much the same kind of behavior. Of course, not going to be, there's only fewer, well, there are fewer changes of concavity here, you know, concave down, concave up. Compared to cubing, because we go only up to 1, there is going to be a change of concavity that is going to be shown, but whatever happens here will happen there in the opposite direction. What I'm trying to say is that whether you integrate sine x dx from 0 to 2 pi, or you integrate sine cubed x dx from 0 to 2 pi, as long as we do a whole period, we're going to be ending with 0, not because the areas, the corresponding areas are the same, not because of that, but because whatever this is, it will undo, or this one will undo this one, whichever way you want to look at it, just as those two undo each other because of the symmetry, not because the areas are the same, or the integrals. So here, oh, that's with sine. With cosine, let's try to squeeze that in here. So a single cosine of x from 0 to pi has this shape. The cosine cubed of x will be same kind of situation as here. This is only to pi. So if we integrate cosine of x from 0 to pi, or cosine cubed of x, because the cube preserves the sign, whether we have a positive output or a negative output, we're going to end up with the same kind of situation. Again, I'm not stating that this guy is equal to that. No. What I'm saying is that those two undo each other. They add up to 0, and so do those two. So every time you have a cosine cubed of v from 0 to pi, we're going to end up with 0. This will not be 0, though, but this part will be 0. 0 for that. Sine cubed, we have a cosine cubed again here from 0 to pi. The other guy is going to be independent with respect to, no, sorry. The 0, well, both of them are going to be 0 in this case. Sine is 0 from 0 to 2 pi. And cosine from 0 to pi will be 0 also. So we got a double 0, multiplication of zeros. Sine of v, oh, good. Sine of v, v goes from 0 to 2 pi. V goes from 0 to 2 pi. Sine, so we have this situation. We're going to end up with 0. Let me double check a few of this. That one won't be 0. This one won't be 0. V, cosine cubed from 0 to pi, 0. Yep. And V, oh, V goes from 0 to 2 pi. Well, we got double this situation. So that one is 0, 0. And let me double check this guy. Sine from 0 to pi. Yep, no, this one is not 0. Take that back. Because sine from 0 to pi is actually 2, I believe. It is not going to give us 0. So that one is not 0, but this one is going to be 0. So I am taking a little bit of a shortcut here, because I know those two are going to split because they're independent of each other as far as the integrals go, and so are those and those. And then one is a constant relative to the other. So this is a constant relative to v, for instance. And then some of them are going to be 0, and all of that is going to be equal to 0 at the end. Whoa. Yes, so we end up with 0 if we do the double integral over the surface. Now, we did not use the divergence theorem. What does the divergence theorem entitle? So example 2, again, with divergence theorem. So remember, we are doing the double integral over the unit sphere of x squared, y squared, z squared with respect to the surface. Divergence theorem says, well, why don't we do the triple integral of 2x plus 2y plus 2z over the volume of the sphere, the unit sphere. So we would have to do a triple integral. We can change that. There's a 2. We can factor out the 2. We can change that to a spherical coordinates. So we would have, spherical coordinates. Let me make sure there's different ways to come up with. So rho cosine phi sine of theta, rather cosine of theta, plus rho, I guess we could have factored the rho because everybody's going to have a rho. Cosine of theta, sine of phi, this should have been sine of phi. This look. Sine phi, because here we have to have sine phi again, and then sine theta plus z, which is cosine of phi. But then we have to multiply by the Jacobian, since we are changing from Cartesian coordinates to spherical coordinates, and the Jacobian will be r rho cubed sine phi with respect to rho, respect to phi, respect to theta. So this is one long integral. Rho goes from 0 to 1 because we are doing spherical coordinates. Phi is going from 0 to pi, and theta 0 to 2 pi. Okay, we can factor out r cubed. I'm sorry, again, this is supposed to be r squared. I was one step ahead. So this portion is the Jacobian. And the reason why I was getting ahead of myself is because there's one row, there's a row here that I was missing, that factors out of all of those. With this row, we're going to end up with rho cubed, and that is going to be independent of the other two variables. So we have 2 times the integral of rho cubed with respect to rho from 0 to 1. All right. And then we have the double integral. So the rows are gone, and we have sine phi cosine theta. Oh, sine squared of phi, because we got 2 of those. We got to multiply with the Jacobian. Here, again, plus sine square of phi, and then sine of theta, plus sine phi cosine phi. D phi, d theta, as phi goes from 0 to pi, and theta goes from 0 to 2 pi. Okay, so we got 2. This is going to be rho to the 4 over 4 from 0 to 1. So we end up with 1 over 4. So that's all of this becomes 1 over 4. All right. Now, if we integrate cosine and sine are going to be, well, not cosine, phi and theta are independent of each other. Technically speaking, we have to break this up into 3 integrals, and then each one of those integrals gets broken up. Well, this one doesn't, but those two get broken up into 2 integrals. So we end up with 5 subintegrals by multiplying and adding. But let me tell you the bottom line. Okay, this is going to be some number. Actually, I know what that number is, but cosine of theta, if we integrate from 0 to 2 pi, the cosine of theta, we're going to end up with 0. It's a whole period. So this part is going to be 0. This one won't, but that one is. So they multiply it out to 0. Now let's do the same thing with the sine of theta. That's going to be 0. Sine phi from 0 to pi, phi goes from 0 to pi. That's not going to be 0, but the cosine from 0 to pi will be 0. So in each one of those cases, oh, wait a minute, that's the same phi. We cannot split it up so easily. Whoa. No, I'm going to put a question mark. 0, I don't know. The first two are fine, no problem. But then, so we're going to end up with times 0 from here, plus another 0, plus, so this is, we're integrating phi. So theta is just, we can split this into 1 and a function of phi. So when we integrate 1 with respect to theta, we end up with 2 pi. 2 pi integral of this with respect to sine phi, cosine phi, d phi from 0 to pi. Yeah, we got to do this very, very carefully. Close the parentheses that we studied here. So those two simplify, and there's another 2 pi. So 2 times 2 is 4, divided by 4, we just end up with a pi. And then we have the integral of sine of 2 phi over 2. That's trigonometric identity. The sine of 2 phi is sine of, rather, 2 times sine of phi cosine of phi. So by dividing by 2, we are good. From 0 to pi. Okay, but think about that. 2 phi, or you can just do the antiderivative, but let's think this geometrically. 2 phi means that we have 2 cycles by the time we get to 2 pi. So 1 full cycle by the time we get to 2 pi. A full cycle, which means that's going to be 0, because that matches with that. 1 is positive, 1 is negative as far as integration goes. So yeah, we end up with pi over 2 because the 2 factors out, but times 0, so we end up with 0. Whoa, it looks like either way we would be doing a lot of work. Whether we apply the divergence theorem to figure out the flux, which means change into a triple integral, or if we actually do the flux directly, both are going to be a lot of work. We're going to end up with 0 either way, although I didn't necessarily knew in advance that we're going to end up with 0. Again, practice both ways of the divergence theorem, just like with Stokes' theorem. Practice both ways so that we have a better handle on what's going on. This was example 2. Where did we finish example 2? Here. We did finish it. The difficult part in example 2, in my opinion, is to come up with a cross product of the parametric function that describe the total surface. I think that's a lot of work and a lot of details to pay attention to. Once we get to this point, then we can start seeing the end of the tunnel, although we still have to carefully go through those factors very, very carefully, because um, if if we put something that is a zero where there shouldn't be, as I was anticipating in this case, then that makes the argument possibly incorrect, or at least, no, it would be incorrect, even though the answer would be accurate. We want to make sure we have correct thinking throughout the whole problem. Um, yeah, yeah. So this whole thing, I think this is easier with the divergence theorem. But again, uh, it's not necessarily clear which one will be easier until we start working on each one of the problems. Um, practice, practice, and practice some more as you do this. Um, divergence theorem. A lot of books of calculus have the divergence theorem as one of their sections, and you can easily just go into the problems of that section and practice a whole bunch of those. All right, with this, we will stop the video now.